Okay, we should probably get started since we've got plenty to do today. Now, a word about next class. So today we're going to finish the material for chapter 6, which is applications. And our next class on the syllabus, the course calendar, it says review. Now here's what's going to happen. So I want you to know so you're ready. We're going to do a practice test, which will take probably about the first 35 minutes. So when you come, be ready to take a test. So you get to experience what a test will be like. So that means get here, be in your seat, have your writing utensil ready, have a basic calculator, 4-function calculator ready, and we'll start. After 35 minutes, then we'll go over the test, talk about the answers, we'll talk about how we would grade and things to look for. So this should hopefully give you a good sense of what's going to go on. And I will say that the practice test is actually a lot of fun. After I wrote the practice test, I thought, wow, this is so cool. It's almost as good as the test. But, the test is also very good. You will get a very reasonable sense about what the test is like because it's the same format, same instructions, same number of questions, same general category of questions. Of course, won't be exactly the same. I don't do practice tests like some people do. Some people say, look, here's a practice test. I'll just change the numbers from the real test. No. The real test is going to be different. Okay, so that's what you have to look forward to on Friday. But let's talk about today. Or rather, I should say, let's talk about last time. So last time we did applications, and really we should say applications for physics. So we talked about work. Now work is a very straightforward thing to compute. It's force times distance. Now, I say it's straightforward, assuming your force is constant, then you multiply. Easy. But what if force is not constant? Well, we do what we always do. Break things into little tiny pieces. And so we break our parts up. So when you see this f of x dx, you should think of, I'm doing my little bit of force over a little bit of area. So that this term here, f of x dx, is a little bit of the work. And then you add the work all together. Now there are a couple things to know. Hooke's law says that if you have a string, then the amount of force it takes to stretch it past its natural length, where x is how far you've stretched, also similarly how far you've compressed, is force equals k times x. Another one, and this one has shown up on many departmental midterms in the last few years. In fact, I think every departmental midterm had one of these problems. That was before I got here. But it's a good one to know. Emptying a tank. How much does it take to move things to the top? Well, what do we have? Well, we have the weight of the fluid in the tank, and we want to take that and lift it up to the top. So there's an h of y. That's how far we have to move up a bit of the water. Well, how much water is there? How much weight is there? Well, the idea is we're really going to think about taking things as a very small, thin slice. So I'm taking a really small bit of the water here. So it's like I've come here and I say, look, how much of the work do I have to do to lift that little bit of water? Well, I have to figure out how much water there is. So that's the area of the cross-section times dy, which gives me my volume of my slice. Now that's not my weight, that's my volume. But when I multiply it by my density times volume, that is my weight. So it's the weight, how far you have to move it up. That's my little bit of work to move that little bit of the water, and I add it up over all of those, which is integration. And the last thing which we mentioned is fluid force. And this is how much is pushing against a plate. So how do you find that? Well, you figure out your density times your area. But the problem is density varies. Density will vary with it's your pressure times your area. And pressure varies with depth. So what you do is you say, okay, I have one term, which is my pressure. There's my density, which is fixed most of the time, unless you have some sort of strange fluid, and how far down you are. So the further down you go, the more pressure you feel. And as they say, under pressure, because you're down there. Okay, all right. Now, That's pressure. Then you times it by your area. So you're thinking about just a little bit of area down below. So you should know these formulas. Hooke's law, not that important to memorize, to be honest with you. But definitely, you should know work is integral force. Definitely, you should know how much work you have to do to empty a tank. And if you have a few brain cells left, you should know how to compute fluid force. Okay, so now we're on to the last application we're going to talk about. That's not to say that this is the end and no other application involves integration, but rather this is the end of what we want to talk about. Okay, so what is it? Well, it's mass. Okay, so our application we want to talk about is mass. And so the question is, suppose we have a one-dimensional shape. And the way you should think of a one-dimensional shape is essentially, look, it's a rod. And you just need to know how far along you are in that rod. So I have this rod going from x equals a to x equals b. And I want to know how much mass is there. Well, let's suppose for a moment that the rod has constant density. Now, density is how much mass there is for a unit of length. So then the mass is the multiplication of density times length. Easy, because it's density is how much mass per unit length. B minus A, how much length do you have? Multiply them together, that's the mass. Now, that's if you have a rod with constant density. Well, what if you have a rod that doesn't have constant density? In other words, as you go to different parts of the rod, perhaps some parts are thicker, or perhaps they use a more dense material, and so you have that the density is varying along the length of the rod. Well, what do we do? The answer, what we always do. And what is it that we always do? We break things up. So instead of thinking of it as a big rod, we think of it as lots of little teeny rods sort of pieced off. So I take my rod and I break it up into pieces, and I say, okay, how much mass is in each little tiny piece? Well, because I'm breaking things into little tiny pieces, I can assume my density, I can treat it like it were a constant. So that I have the density of that little tiny piece, that's my delta xi. I have the length of that little tiny piece, that's my delta xi. So this is my mass of my little piece. And I add them up. But of course, you say, look, just go finer and finer. And your summation becomes the integral. The integral from a to b of delta x dx. All right, good. Well, let's try an example. I have a rod, and it has a density of 1 plus 2x. So this is a density which varies. And this happens to be a rod with length 2. The question is, what's the total mass? Well, because I have my density, and I know that mass is the integral of density, this is going to be a not unreasonable problem. Now my bounds are given to me, 0 to 2. So 0 to 2. So integrate 0 to 2, and 1 plus 2x dx, and we integrate. That one, okay, this one I can do. I've been practicing these. X plus x squared from 0 to 2. And if we plug that in, then we get 2 plus 4 minus 0 plus 0, and therefore our mass is 6. Now, 6 what? Well, 6 whatever you're choosing to measure your density by. Oftentimes, we use kilograms. Kilograms is a fairly nice measurement of mass, different from pounds. Pounds is actually not a measurement of mass, but that sounds like a physics discussion, and I'm not a physics person. So let's move on. Okay, so mass, very straightforward. Mass, you integrate density. All right. Well, let's talk about the center of mass. Now, people have a couple different views on what we mean when we talk about the center of mass. Now, most people will say, look, the center of mass What is that? That is the point where you could balance things. So in other words, if I were to put my finger right underneath that center point, so I have this rod, and I put my finger right underneath the center point, then it won't tip over. It'll exactly balance out. How do you find the center of mass? Well, if you have a constant density, it's easy. It's in the center. It's a good name, the center of mass. It's in the center. Now, if you have varying density, well, we might shift. So here, I'm drawing a picture where I'm using sort of the thickness to indicate mass. So I have a rod, which at one end is very thick, and then it becomes very thin on the other end. And so, well, there's more mass here on the left-hand side. So the center of mass should be shifted towards that point. All right. Now, I have a word of warning here. When we talk about center of mass, you might say, okay, the center of mass, that's the point where half of the mass is below and half of the mass is above, which is a very reasonable way to think about center of mass. It's like, where's the dividing line? Half above and half below. But that is not what the center of mass is measuring. It's measuring something else. So when you talk about the center of mass, well, the way I like to think about it is I really like to think about it as a weighted average. And we'll talk more about what this is. We'll see an example of how what we're going to give as the center of mass is not the same. By the way, if you're ever curious, suppose you have an object and you want to find the center of mass, there's a really easy way to do that. What you do is you hold the object, you put it on your fingers, and then you just start moving your fingers together. And what will happen is that as you move your fingers in, it will actually zero in on the center of mass. You should try it. It works surprisingly well. Okay, well, this says what the center of mass isn't. Maybe we should talk about what the center of mass is. Okay, so I'm going to give a very simplistic example. So this is very discrete. This is not the kind of problem we have, but imagine that I have a few pieces of mass. Say I have 2 units of mass at 0, 5 units of mass at 4, and 3 units of mass at 5. And what I'm after is the average. And I call it the weighted average. Now I say weighted because when you have more mass at a point, you should be more important. Well, how is this computed? What you do is you multiply the mass at a point times the location of the point. So 2 times 0, 5 times 4, 3 times 5. So 2 times 0, 5 times 4, 3 times 5. And you add all those numbers up. And then you divide by how much mass there is total. So 2 plus 5 plus 3. 2 plus 5 plus 3. Now if you do the computation on the top, you get 35, and on the bottom you get 10. 35 over 10 is 3.5, which would say that the center of mass is right there. Now, to help you sort of get an idea of what's going on, let's think about this in a slightly different way. Let's suppose we had a quiz, and the scores that were possible were 0, 1, 2, 3, 4, or 5. Now, on that quiz, 2 people scored a 0, 5 people scored a 4, and 3 people scored a 5. What would be the average score? Excuse me. Well, what you would do is you would add up all the scores. So you'd add up 2 zeros, you would add up 5 fours, and you'd add up 3 fives, which is what's happening here. 2 zeros, 5 fours, 3 fives. And then what you do is you divide by how many people there were who took the quiz. 2 plus 5 plus 3. So if we were thinking about this in terms of that, finding an average of scores, this is exactly what computation we would do, and we would get 3.5. So it's this sense of average that's happening. So in particular, what we're going to say is that we're going to look at the following expression. we have the sum of the x-coordinates times the mass. Now we're going to call this the moment. And why do we call it the moment? I have no idea. But we do. That's the term for it. So when you take physics, you'll talk about moments. You can talk about first moments and second moments. If you take statistics, you'll talk about moment-generating functions. So it's a very standard term. I don't know why, but that's okay. That's the numerator. In the denominator, we are going to sum the masses. And so to find the average, we take the ratio. So we take the moment divided by the mass. Now we abbreviate things. The moment, we call this m0 for right now. And the mass, we call that m. Now, it's not hard to see why mass should be called m. And moment, m for moment. What's the 0? Well, when we talk about moment, it's really, when we say moment, it's with respect to something. And in particular, it's with respect to some location. So here, the moment is with respect to the origin, with respect to 0. How far are you from 0? So that this entry here, this x sub k, that's really talking about distance. How far are you from where you're measuring? So we're going to do a few other things as we go on, but you should think about this notation here as saying, where are you measuring it with respect to? In one dimension, it's very simple. The measurement with respect to 0, and the distance is just the x-coordinate. Now we can do integration, which says, well, look, just keep refining finer and finer. And so in general, we have that the x bar, that's the center of mass for this rod, the ratio of two integrals. It's the integral a to b of x delta x dx, and again, this is our moment, over the integral a to b of delta x dx. All right, a weighted average. Weighted average. All right, good. Now, any questions on that? Let's try an example. Here's an example. Let's find the center of mass for a rod with density delta x equals 1 plus 2x, where x goes between 0 and 2. This feels very deja vu-y. Have we seen something like this before? Yes. In fact, we had this problem a few minutes ago which says, look, you have this rod with density, delta x equals 1 plus 2x, where x goes between 0 and 2, and you have to find the total mass. And we found it. It was 6. Okay. So we can save ourselves a little bit of work and just say mass, which is the integral 0 to 2, delta x dx is equal to 6. All right. So we're halfway there. We're halfway there. Now, why do I say halfway? Well, when we're looking for center of mass, we're looking for this, what we call x. Oh, by the way, I forgot to say, this thing right here is a bar, x bar. And so when you see a bar over a symbol, it means an average. So think of it as it's the average x. So we're finding the average x. So we need to find now the numerator. Okay. So I need to find m0. m0, that's the integral 0 to 2 x delta x. Okay, well, let's do the computation here. Okay, so that's integral 0 to 2 of, I know delta x is 1 plus 2x, so if I multiply this out, I get x plus 2x squared dx. Okay, this one's a little bit harder. What's the integral of x plus 2x squared? 1/2 x squared plus 2/3 x cubed. All right, evaluate from 0 to 2. Okay, so that's 1/2 times 2 squared, that's 2. It's not bad. 2/3 times 2 cubed, 16 over 3. And when I plug in 0, I get 0. Okay, 2 plus 16 over 3. Well, the 2 is 6/3. And yeah, so 2 is 6/3. 6/3 plus 16/3 is 22/3. Now, we take our average. Well, what do I mean? I take the 22/3 and I divide it by the 6. So I get 22/3 divided by 6. Or that's 22/3 times the 6. Now I can do a little bit of math. For example, I can divide out by 2. So I get 11 on top and 9 on the bottom. So I get 11/9. Okay, now at this point, most people would say, good, we're done. Let's move on. But let's just take a second and think about what's happening. Is our answer reasonable? This is always a good thing to check. It's amazing how often people don't stop and say, I wonder if this is a reasonable answer. Well, let's think about what's happening. If I think about it, I have this rod, and it's getting a little bit thicker as I move from left to right. So a little bit thicker, not too dramatically. So here I have 0, here I have 2. Roughly speaking, where is 11/9? A little bit above 1. So if here's 1, 11/9 would be over here. Now, notice a couple of things. First off, it's moved towards the heavier side, so that's good. This is reasonable. But the other thing you should notice is it's actually in between 0 and 2. If we had done our computation and somehow we got to the end and we say, the average is over here at 4. What should we say about that answer? There's a mistake. Your center of mass can't be to the point where all the mass is on one side. That's not very centered. You want to have a centered approach. So just check to make sure, is your center of mass actually nearish the center? And if it's off to one side, that's unreasonable. I taught trigonometry once, and I had a question about finding the height of a mountain. The answer was, I think, 2 miles or 3 miles. Somebody got the answer, 24,000 miles. And I thought, wow, that's like a tenth of the way to the moon or something. It's a ridiculous answer. But they didn't even stop to say, this is a ridiculous answer. I should probably check. So be reasonable. Now, I said a few moments ago that the center of mass is not where 50% of the mass lies. Let's see if that's true. So how much total mass is there? There's 6. So suppose I want to find the point, where does half of the mass lie? By the way, I have no idea what the answer is to this, but we'll have fun. We'll figure this out. So if I want half the mass, what I want to know is how much of the bar do I have to go? So I'm going to think of the following. I'm going to integrate from 0 to some point A. And I'm going to integrate my density. So what is that telling me? Well, it's saying I want to figure out what A is. So that's trying to find where is the halfway point for the mass. Where does 50% of the mass lie? Well, if I want to figure that out, I just do the integral. 0 to A of 1 plus 2x dx, which is x plus x squared evaluated from 0 to A. Well, that's not bad. That's A plus A squared. So what am I looking for? Well, I'm looking for A squared plus A minus 3. When does that equal 0? Now, most of you who have had me will say, well, it must factor. This does not factor. So how do we solve for A? Yeah, the quadratic equation. A would be -1 plus, and I don't need to worry about -1 minus, because look, -1 minus, that's definitely super negative, and we can't have a negative 50% point. Okay, so -1 plus square root of b squared 1 minus 4ac. Well, that's plus 12 all over 2, which is square root of 13 minus 1 over 2. Well, square root of 13 is, I don't know, about 3.5 or so. 3.5 minus 1 is about 2.5. So roughly ballpark 1.25. So, but you'll notice the important thing is square root of 13 minus 1 is not 11/9. And so the place where 50% of the mass lies is not your center of mass. That's the take home. And now you're probably thinking, wow, center of mass is probably going to be a lot easier than doing the place where 50% of the mass lies. Yes, it is. It's really hard to do these kinds of things. So don't do that. Don't do that. Do the right things. Do the right things. Okay. Well, that's center of mass if we had a rod. What if we had a 2-dimensional region? Okay. Let's see if I can get this on the screen without injuring myself. So here we go. Here we have a nice 2-dimensional region. And I want to find the center of mass. And I'm going to think about this region as being bounded. And in particular, I have a top curve, y equals f of x, and I have a bottom curve, y equals g of x, and I have a density function. And I'm going to assume the density only depends on my x coordinate, so that as I move along in the x direction, it varies. What that really is saying is, look, if I go up and down, it's the same density everywhere. Now, what if I want to have density vary with both x and y? Ah, that's good. Next semester, Calc 3. It'll be fantastic. You'll get all sorts of things. It'll be cool. Okay, so the question, same question as before, how do we find the center of mass? And the answer is we do the same thing as we've done in the past, which is we say, well, look, let's really think about breaking things into parts. So I'm going to think about breaking things into this strip. And I've marked here this strip and say I can really approximate this strip by a rectangle. So I have this small rectangle, and the width is, as almost always is, it's a small change in x. And if I wanted to ask, what's the center of this small rectangle approximately? Just if I wanted to know what the center is of a small rectangle. And the answer is, well, I can figure out what the center is because it's very, very thin, so it's just the x-coordinate. That's an approximation. It doesn't have to be very precise. So that's the x-coordinate for the center. And again, I'm just focusing on this very small rectangle. And rectangles are nice. Because it's a thin rectangle, I can assume my density is constant. If I'm looking for the center of mass of a constant density rectangle, I go to the center point. Okay. So the center for the x-coordinate, that's just x. How about for the y-coordinate? Well, now the y, the top and the bottom, can be very different. See, the left and right are going to be very close together. That's a very small, tiny change in the x. But the top is a big change. So to figure that out, I say, well, it's halfway between the curves. How do I find that? I average. So I take the top plus the bottom and divide it by 2. So I get 1/2 f xk plus g xk. Okay. Now we're going to throw a lot of formulas at you, but if we just relax, we'll see that it's really the same philosophy that we've already had. So it's actually nothing new, which is good, because that means we can relax. What's happening? Well, first off, I can talk about mass. In mass, I didn't write this down, but why didn't I write down mass? That's ridiculous. Okay, let's pretend like I can write mass somewhere. Let's suppose, let me choose a different color than green. Mass. Well, what is that? Well, it's approximately the sum over k, my density times my height times my width. Now, why do I say that? Well, the density times my height, my height times my width, this f minus g delta, that's the area, delta times area is mass. So the delta times F minus G delta, that's the mass of a little piece, and I add them all up. And this becomes the integral from my bounds A to B of delta times F of x minus G of x dx. Sorry, forgot to write down the equation for mass. So we're integrating delta times F minus G. For the moment, we need to talk about with respect to what? So we're going to have two kinds of moments. One is with respect to the y-axis. One is with respect to the x-axis. And so we have these two expressions here. Now, here's the thing to remember. When I talk about the one with respect to the y-axis, and so that's what the subscript y here, m sub y says with respect to the y-axis. If I'm at a given point x comma y, how far am I from the y-axis? Well, square root of x squared plus y squared is how far I am away from the origin. How far am I away from the y-axis? So in other words, here's my question. Here's a point, x comma y. How far am I from the y-axis? X. So when we talk about moment with respect to the y-axis, I'm going to use this x value, because this is distance to y-axis. So the moment always has a notion of distance built into it. So what I'm going to do is I'm going to add over all k. Then I'm going to have the distance where I'm at, in this case distance with respect to the y-axis, and then the mass of the little tiny strip, which is, as I said, it's this part over here. So that we get that the moment with respect to the y-axis is equal to the integral from a to b of x, the density of x, which can vary, the height, the difference, f of x minus g of x dx. The moment with respect to the x-axis is going to be similar. So let's go back to this question. If I am at a point x comma y, how far am I from the x-axis? Y. So when I talk about the moment with respect to the x-axis, I need to figure out how far I am from the x-axis. Now here's where it gets a little bit subtle. You might say, aha, this part should be y. And it is. Why? It's coming from there. Because I'm thinking about where's that center point at. The center point is the halfway point. So that's the y coordinate, is that 1/2 f plus g. So with the moment with respect to the x-axis, I have the distance to the x-axis, which is the center, times the density times the area. So delta times area is the mass. So now we get a little bit interesting expression. The 1/2 comes down, the density comes down, and then f plus g times f minus g. Well, f plus g times f minus g, that's one of those nice things from algebra. A plus b times a minus b. A squared minus b squared. So that these two pieces combine to give you f squared minus g squared. So that's what happened to that. So now, once you have done those three pieces, you've done the moment with respect to the x-axis, the moment with respect to the y-axis, and the actual total mass. The x-coordinate is the moment with respect to the y-axis over m. And the reason why it's a y is because I'm thinking of weighing it according to the x's. The y-coordinate for your center of mass, your y bar, it's the moment with respect to the x-axis over m. And that's because we're weighing it according to the y-coordinates. Okay. There's a lot there. Any questions? And then we'll do examples. Lot to learn, lot to learn. Okay, let's try examples. Now, suppose we have the following. Find the center of mass of the region, 0 less than or equal to y, less than or equal to 1 minus x squared, given that the density is constant. Now, let's talk about what our region looks like. So first off, I'll draw my axes. So I have my axes. This expression says I'm between two parts. I'm above 0. I'm below 1 minus x squared. Now, above 0 just says, okay, I'm up here, the top half of the plane. What does this 1 minus x squared look like? It's an upside down parabola where I've shifted it up. So I'm in the top half of the plane, but I'm also below this parabola. So our region looks like this. And we're asked to find the center of mass for this expression. And we're told that the density is constant. Now, I claim this is half of it is pretty easy. Which half is easy? Sorry, what? Well, no. When I say half the problem, remember I have to find the center of mass. The center of mass is going to be a pair of points, x bar, y bar, which is going to be a ratio of m sub y over m sub x over m. And I claim half of this is easy. Why is x bar easy? Okay, so notice that there is symmetry here. So in other words, it's symmetrical. Now, most people will say, cool, that's totally obvious. But there's a subtlety. Okay, all right, because we know we love subtlety. What's the subtlety? How many symmetries do we need in order to claim that we have symmetry? What has to be symmetric? Now you're nervous because you're like, he's trying to trick us. I'm not trying to trick you. Just give me something that has to be symmetric. The density has to be symmetric. That's the one that people forget about. The other thing that has to be symmetric is the shape. So you need a shape which has symmetry, and you need a density which has symmetry. Now what I mean by the shape that has symmetry, well, if you turn it and flipped it like this, you get the exact same shape again. That's what we mean when the shape has symmetry. The density has symmetry says, look, if I do this flip action, then the density here, when I flip it over, it still hasn't changed. So in other words, the density agrees across the line of symmetry. Now when your density is constant, you just look for symmetry in the shape. If your density is not constant, you have to check, well, hold on, if I flip across that line of symmetry, am I going to preserve the weight? Am I going to preserve that density? And this time we do. So we can use symmetry, and what's true is that center of mass, this is a very nice result, lies on any line of symmetry. So occasionally, you might even be able to get the whole center of mass by just saying, look, here's two lines of symmetry. They cross. That has to be the point of symmetry. Now, usually we won't do that. We'll make it more interesting for you. But one thing that this does is it helps you narrow down the problem. And so, by symmetry, we can conclude that the x-coordinate is 0. All right, so we're halfway there. But what's left? The y-coordinate. Okay, so let's set up our integrals. So mass is going to be the integral -1 to 1, because those are the bounds of my region. Then I'm going to have my density. And since density is constant, you just pick a constant. Sometimes people just say, throw in a value c. It doesn't matter what the density actually is. So let's just assume it's 1, just to help simplify our computations, so we don't have numbers floating around. And now what goes next? Well, it's the top minus the bottom, which is 1 minus x squared. And, well, I should say 1 minus x squared minus 0. So the top function is 1 minus x squared, the bottom function is 0 dx. So this is not bad. So really this is just saying negative 1 to 1 of 1 minus x squared dx, which is x minus 1/3 x cubed from negative 1 to 1, which if you work this out, you'll get 2/3 minus negative 2/3, giving you a total of 4/3. Okay, so that's mass. All right. Now, we have to do the other part. So we have to find m sub x. All right. So I'm going to pull up my handy dandy guide here that says m sub x, so it's going to be 1/2 the density, the top function squared minus the bottom function squared dx. All right. So that's going to be 1/2 times my density times 1 minus x squared squared minus 0 squared dx. Or integral negative 1 to 1 of 1/2 times 1, multiplying this out, minus 2x squared plus x to the 4th dx. Okay. By the way, I can just make an observation here. What kind of function do I have? It's an even function. A polynomial, you can tell if it's an even function if all the powers are even. It's an odd function if all the powers are odd. So since it's an even function, and I'm going from negative 1 to 1, I can go from 0 to 1 and double. So this is 2 times 1/2. It's just be 1. 0 to 1, 1 minus 2x squared plus x to the 4th. Okay, so we're almost done. So that's x minus 2/3 x cubed plus 1/5 x to the 5th from 0 to 1, which will give me 1 minus 2/3 plus 1/5. And then subtract off 0. And if you put that all together, common denominator is 15. So it's 15 minus 10 plus 3 over 15. 15 minus 10 plus 3 is 8. So we get 8 over 15. Now, it's not quite the center. Now we need to take the ratio. So y bar is m sub x over m, which is 4/3 over 8/15, or if you like, 4/3 times 15 over 8. 3 goes into 15, so that goes in 5 times. 8 goes into 4, well, that goes in twice. Oh, sorry. Yeah. Okay. 8. I already caught it. 8 over 15 over 4 over 3. Okay, thank you. Well, I was going to say, I obviously had made an error there because I was getting a number way too big. 8/15 times 3 over 4. Again, I can go 5 times, and here I can go twice. And so I get 2/5. Okay, so therefore, our center of mass, x bar, y bar, is 0,2/5. Done. Easy. Yes?
Didn't you have to double the select value and you got the balance from negative 1 to 0?
I did double. Notice that I had a half before,
Oh, got it.
and the half is gone. 2 times a half. So I did double. I doubled down, as they say. Okay, now let's try a quick change. I won't go through the whole problem. As you can tell, these take time. And you're probably wondering, do we have a center of mass problem on the test? Probably do. So let me just talk about this for just a moment. I won't go through and do the whole computation, but I want to ask the question. This is the same region. 0 less than or equal to y less than or equal to 1 minus x squared. So we have the same basic shape. Do I have symmetry? Well, The shape, yes. But notice what happened from this problem. It's the same shape, but density is now different. What's happening here is that the density is going to change. So on the far left, the density is very small, 0. If we were thinking this as a plate, it'd be basically going off to a point. And now over on the right, the density is increasing. So if we think about this as though thickness were density, it's increasing. So it's very thin on the left, very thick on the right. So we have the shape has symmetry, but the density, no. So what does that mean? It means that we don't get free points. We actually have to compute x bar by doing the whole computation. In the interest of time, I won't do that, but I will post what happens with that. Now, finally, let me just mention 2 more things. And to help put your mind at ease, I will not test you on the following. We can repeat this whole discussion about mass, center of mass, and instead of doing a 2-dimensional region, we can do a line. The way you should think of it is, now I'm trying to find the center of mass of a rod, but it's not a straight rod. It's a bent rod, and it has a shape. And so how can I find the center of mass? Well, let's just think about it in pieces. How do I find mass? Well, mass will be density times length. And so whenever you see the expression square root of 1 plus f prime of x squared, that basically always comes from a length. Times dx. This is a length. It's the length of the curve. So I'm taking length times density, that's a little bit of the mass, and then I'm adding them up. And now if I want to find the moments, I do what I did before. When I talk about moment with respect to the y-axis, I multiply by x. When I talk about moment with respect to the x-axis, I multiply by y. But y is f of x. And then we can find the center of mass, x bar, y bar, which is these ratios, m sub y over m, and m sub x over m. Now, I won't test you on this, other than there's a quiz problem about mass. So you'll get to do a quiz problem. So it'll be fun, but it won't be on the exam. One last thing. Why do we care about centers of mass? Well, the nice thing is, when you have a center of mass, it oftentimes allows you to take your object and contract it down and treat it like a single point. So for example, when you do models of a solar system, you don't think of the sun as this really big object. You think of it as a single point which has a lot of weight. And you treat each planet like a single point which has a lot of weight, and then you run the simulations. So there's an example of this in geometry. This is Pappus's theorem. Pappus was a Greek mathematician, and said, look, suppose I want to find the volume when I spin an object around an axis. How can I do that? Well, the key is to say, think about where the center is of that object. And in particular, how far is the center of your object, in this case, you think the center of mass, how far is that from where you're spinning? And then what you do, that number you call rho. The volume will be 2 pi rho times the area. So, as a quick example, and I know we have time, I know you're very anxious to get out of here and play in the snow, because you've been missing snow. You signed up for Iowa State just so you could experience these lovely winters, and you're like, where's my winter? You know? Suppose I had a circle of radius 1, centered at 2, and I spun it around the axis here. And I wanted to find the area. Now, this is a problem that we did. This is the Homer-Simpson problem, where you had to find the volume of a torus. Let's think about what this theorem says. Well, it says, figure out a couple of things. First off, 2 pi is 2 pi. So that's 2 pi. Rho, well, how far is it to where we're spinning? And the answer is 2. Because the center of the circle is the center. How much area does the circle have? Unit circle, radius 1, has area pi. 2 pi times 2 pi gives 4 pi squared. And that's the answer. We actually did that. 4 pi squared was the right answer. So this is an example of Pappus's theorem. There's also one for surface area. I won't test you on that because it's more fun to test you on integration. But it's good to know. All right, we'll stop here and see you on Friday. Be ready. to be tested, because you will be tested.